So, to begin, we ask a question. Just what is sound? Well, sound is a compressional vibration, and it propagates in an elastic medium. And sound is a wave. No material transports from one place to another by the sound itself. So for our ears, that elastic medium is a gas. It's obviously air. How sound is made is what's crucially important to what we're talking about today. And it can basically be made by three different actions. You can vary the mass, and for example, that's how rockets and sirens work. That's why they're so loud and effective. You can move surfaces like loudspeakers or vibrating equipment panels. And finally, you can vary the energy in airflow by causing turbulence. Primarily, the causes of HVAC noise are the latter two, moving surfaces and air turbulence. Now, sound propagates at a fixed speed through the air. For those who like imperial units, it's 1,150 feet per second or 343 meters per second. That's roughly constant. And that's what people are referring to when they say the speed of sound, or Mach 1. It's about 767 miles per hour. Another important feature of sound that we always need to keep in mind is that it can bend around corners and squeeze through gaps. And this is one of the key reasons why noise control for HVAC equipment can often be very, very challenging. Let's move on to describing sound. How can we technically describe sound so that other people will know what it is we're talking about? So first of all, let's talk about what metrics describe sound. Well, primarily there are three: amplitude, frequency, and variation with time. With amplitude, we're basically saying how loud is it and how much does it need to change before I can notice it. And we'll also define just what a decibel is, because there's a lot of confusion around that. As far as frequency goes, that's answering the question of what pitch is it, like touching keys on the piano keyboard. It also has to do with the combination of frequencies that give it a timbre or quality. And we can ask the question, well, how does my ear filter the frequencies of sound? And as far as frequency is concerned, we typically describe it using the quantity hertz, which is cycles per second, and not a rental car company. Finally, we talk about variation with time. How does it change over time? How does sound change and how can it be described? And the image here is actually multidimensional in that it's describing someone speaking, and that's along the horizontal direction, but also all the frequencies that their voice is making in real time show in the vertical direction, and the intensity or amplitude shows up as color. And you can see this is some speech, just how complicated it is in all three dimensions. Let's back up and go through each of these relatively quickly, but in a little more detail. First of all, let's talk about amplitude. Now, again, sound waves are compressional. They compress the air and they pull apart or rarefy the air above and below atmospheric pressure. These changes in sound pressure are really tiny. They're only about 1/millionth of atmospheric pressure. When we talk about amplitude, we're talking about the difference in pressure from the highest peak to the lowest negative peak, or the rarefaction. When we ask what is a sound level, we're taking a root mean square sound pressure. That means an average pressure. So it's basically asking what's the average over time of this going above atmospheric pressure and going below atmospheric pressure. And that's how we get to a sound level. Human hearing has an amazingly wide range of sound amplitudes that we can hear, going all the way down here at the bottom of the threshold of hearing, which is a teeny tiny amount of sound pressure, all the way up to, say, a passenger jet taking off about 100 feet away, which would be very, very painful for the majority of us. And in fact, if we go another 20 dB up to maybe a military jet taking off, now we're talking about if an unprotected ear would be destroyed. What's important to note here is that the amplitudes cover a range of over 1,000,000 from 20 micropascals all the way up to about 20 pascals. And a pascal is a tiny fraction of atmospheric pressure, as I was referring to earlier. So that brings us to the question, just what is a decibel? Well, decibels are a way to compress these powers of 10 going over a range of 1,000,000 down to sums of 10 using logarithms. And decibels are used to define a level. So I'll be talking about sound levels, sound pressure levels, sound power levels. I'll always use the term level to refer to decibels and vice versa. Now, these units were invented at Bell Laboratories, and they are in fact named after Alexander Graham Bell. One bell, or a B, is defined as one factor of 10. And to get a better or finer scale, they divided that by a further 10, so each bell is divided into 10 pieces, called a decibel, or decibel. Formally, a bell is a logarithm of the ratio of the mean square pressure to a reference pressure. So there's the formal definition of it. You can take that home. The reference pressure for sound in air is 20 micropascals. That's basically the lowest possible sound that a normal human can hear. But what's important to note is that decibels are always ratios. It's a ratio of something to something else. So it doesn't stand on its own like gallons or pounds. And this little graph on the bottom corner shows how it ranges from 0 decibels is a ratio of 1, and then every factor of 10, you add 10 decibels. So if I go to a factor of 10 higher, it's adding 10 decibels. A factor of 100 higher, it's 20 decibels, and so on. Let's go back and ask, well, how do we talk about frequency? The frequency of a sound wave is measuring how many times it compresses and rarefies, or cycles, in 1 second. And that unit of frequency is the hertz, or 1 cycle per second equals 1 hertz. Now, our hearing covers a range roughly from a very low frequency of 20 hertz to a very high frequency of 20 kilohertz. Most of us probably can't hear quite that entire range. As we age, we lose quite a bit of that upper range in particular. A low frequency sound has fewer waves per second. So there are not as many waves per second, and they're longer. They're physically very big. At 20 hertz, a sound wave is almost 60 feet long. And even at 200 hertz, which is about the pitch of my voice, a sound wave is 6 feet long. And the size of those waves is part of what makes controlling noise very challenging. High frequency sound has many more cycles per second, and so they're much shorter waves, and they go from about 7 inches at 2000 hertz down to about 0.7 inches, or just over maybe 1.5 centimeters at 20,000 hertz, so very small. Our hearing is actually most sensitive right in the middle of our vocal range, between 250 and 8,000 hertz, with a peak near 3,000 hertz. And we'll see that in effect as a filter later on. When we talk about frequency, we don't, especially with things like equipment noise, we're not just talking about one frequency, but an entire spectrum of frequencies. And complex sounds have a spectrum, just like light passing through a prism can be broken into its frequency components, or colors. So can sound, which has many different complex tones in it, be broken down and expressed in a spectrum. And most equipment noise is expressed as a spectrum in so-called octave bands, where each band represents all the sound energy in that band, and the band goes up by factors of 2. So you go from 31.5 to 63 to 125 and so forth. And they're literally exactly like octaves on a piano. And the value of the octave band is all the sound energy contained in that band. This is important because these are the values used to describe HVAC equipment noise by AHRI standards 260, 270, 370, and others. Sometimes when we measure noise and we're trying to figure it out, we actually use a finer spectrum called a 1/3 octave spectrum. And it's very literally what it sounds like. You take the octave band, you break it up into 3, and then have the sound energy just in the narrower third band. It gives you a little more detail in the spectrum, and it can sometimes indicate where you have tones in your spectrum. When we're really trying to get into the detail of which components are making which noise, we'll use what we call a narrowband spectrum, where each band is an equal number of hertz instead of an equal octave of hertz. And that helps us to exactly pinpoint noise sources. But there's so much detail that it wouldn't make sense to express that, for example, to a client or a contractor or someone trying to specify what they want from equipment, because there's just too many numbers. However, what I've shown in highlight here with the red circles is this is actual HVAC compressor noise, and in the bottom, in the narrow band, you can see the tone of the compressor standing out very strongly. That's the hum that the compressor makes. That tone is also captured here in the third octaves. You can see it's well above its neighbors by several dB. And again, it sort of shows up in the octave band, but as you go up through each, from narrow band to third octave to octave, you see that you lose detail. And that's one of the trade-offs that we have in trying to express the complexity of the noise, the total range of sound that's coming out of a machine, but at the same time keep it simple enough that we can put it in a table in a brochure. When people hear sound, they don't hear it evenly at every frequency. I talked earlier about hearing sound from 20 hertz to 20 kilohertz, but we don't hear them all equally. Our hearing is very weak at low frequencies. It's pretty acute in the mid frequencies, but it's very weak at the high frequencies. But when I measure a sound level with a device like a sound level meter, I include all the frequencies of the sound equally when the sound level meter is running. So we need a way to emulate human hearing so that the number that comes out of the sound level meter is similar to what we're actually hearing. And for that reason, we have these filters called A, B, and C. By far the most common one is the A weighting filter, and dBA is the single number rating most typically used to quantify sound as it's perceived by humans. It integrates all the sound that's in the frequency spectrum, and then it becomes a very common single number sound metric. So most installations would probably give you a metric that we want the sound to be below this many dB. What they really mean is dBA. And that's all the sound blended together, all the energy added up into a single number. Finally, there's the question of sound changing over the time. A decibel is a complete measure of sound if the sound is constant. But what if it changes over time or changes in its frequency content? For those cases, we use statistical energy, sound levels and concepts from the area of sound quality. We can use average levels, something like the equivalent continuous sound level, which is a form of averaging decibels. We can use percentile levels, like day-night, where the nighttime noise has a penalty, or percentiles where you have you ask, well, what level does 90% of the sound go above, and what level is 90% of the sound below? And those can help us understand the impact on the nearby population or the listeners. And finally, there are such things as sound quality metrics. You don't hear too much about them. They're not very frequently used, but they are measurable. Things like roughness, sharpness, fluctuation strength. These are all measures of how the sound is changing in time. So let's delve a little deeper into the human response to sound. First of all, we'll look at our ear as a filter and ask, well, what's the range of audible sound? So, and by audible, I mean audible to a person with normal hearing. Well, as you can see from the diagram, the schematic on the left, the human ear is tremendously complicated, and all these components basically act like transducers, and they filter the sound that comes in. So while my sound level meter is a measurement device and can pick up everything equally, the ear has several mechanisms built in that shade the sound both in frequency and amplitude. So in the diagram on the right, we see that at low frequency, the audible range is much smaller than in the mid frequency where it's many, many decibels. And it's very interesting to note that speech and also acoustical music are right in the middle of those ranges because that's where we're comfortable in listening. How do we express changes in amplitude? Well, we use decibels again, but they don't add and subtract and go up and down the way you might think they do. First of all, it's important to note that twice as many decibels is not twice as loud, and half as many decibels is not half as loud. It's plus 3 decibels to get twice as much sound, and minus 3 decibels to get half as much sound. What that means, for example, is that if I have a condenser fan and it's putting out 75 decibels A-weighted at several feet away, and I add and I add one more fan, so now there are 2 and they're both running exactly the same, the sound level goes up by 3. It does not double, so it won't go from 75 to 130. 150. It will go from 75 to 78. And it's important to note that you need to change a sound level by about 10 dB in order for most people to say, if they were to be surveyed, that it seems twice as loud, or down 10 dB if you want it to be half as loud. And that's counterintuitive, but that has to do, again, with how our ears process sound. It's also important to note that a difference of less than plus or minus roughly 2 decibels is very difficult to perceive, especially if there's time difference, like a before and an after case. If you only change the sound by 1 or 2 dB, your client's not going to really notice it. You really need to make a bigger impact of that if you want it to be perceived. And finally, after all of this talk about sound, we come to a very simple question. Just what is noise? Well, very simply, noise, by most people's standard, it's unwanted sound. It's important to note that noise is a subjective response. It does, in fact, increase people's stress levels, and it can affect their productivity and their health. So it's very serious. Noise is influenced by variations in all the things we've talked about so far. So variations in amplitude or loudness, variations in frequency, both pitch and timbre, and variations in time, things that turn on and turn off. A lot of times you can get used to a sound, but then it'll suddenly go away and suddenly come back, and then it becomes noise. So when someone is speaking to you about sound and they characterize the sound around them as noisy, they're reacting in a negative way to that sound. So let's move on and let's talk a bit about fundamentals of noise control. I just have a couple of slides here that I want so that everyone has a feeling for what's actually happening when you try to control noise. The first thing to understand is that it is best described as a source path receiver model. That's a very fundamental model that says that the sound is coming from a source whose sound power we can describe. It's propagating through some path, whether that's out in space or through a ductwork or through a wall. That's part of the path, and it comes to a receiver. And for our purposes, the receiver is almost always the ears of a human. That's not necessarily always the receiver we care about, but for our purposes, that's the receiver that's most important. This model, source path receiver, is absolutely fundamental to the idea of noise control. Why is that? Because if we want to control the noise that's impacting the receiver, we have to change one of those 3 things. We either have to reduce the source, and you'll note I put 4 out of 5 stars there because reducing the source of the noise is very effective. If you're making less noise, there's less noise to worry about, there's less noise to get the receiver. However, changing the source is typically the most expensive way to control noise, because especially if it's something that's already been installed, trying to change it can be prohibitively expensive. And so your next option is to interrupt the path of sound. I'd say about 90 to 95% of noise control is involved with interrupting the path. It can be anywhere from completely ineffective to moderately effective, depending on the complexity of the situation and the challenges involved in breaking that path. And therefore, it's typically moderately expensive to do a good job. The final way to do it is to protect the receiver. And that's the easiest and least expensive thing to do, but it's also the least satisfying because a couple of things. Number one is I've shown it here as putting, earmuffs on your head or earplugs, and that's protective equipment that's frequently used in noisy situations where there is no other means of protecting people. Another thing you can do is you have what are so-called administrative controls. You control people's time of exposure to certain levels of sound. But in the end, you're not making anything really any better. And so it's sometimes the least expensive. It's certainly not a good resolution if you have customers in an office or an apartment building or some other situation and they're complaining about HVAC noise. You can't simply tell them to put in earplugs. We talked about sources earlier on and about sound power. What about paths of sound? Well, there are three fundamental paths that sound can go through. The airborne sound path is the one we've been talking about so far, and that's where compressional waves are moving right through the air. And they reflect off of hard surface, they diffract around corners and through gaps, but they also decay with distance in terms of their amplitude. In general, higher frequency sound dies away in a shorter distance than low frequency sound. The second important path is structure-borne sound. That's vibration, and that's vibration of solid objects. It's important to note that once vibration gets into a structure, the joints in the structure send the energy in every direction, and that energy will always find its easiest path. Oftentimes we describe that as the water balloon effect because you squeeze a water balloon, you just make the water pop out someplace else. It's often similar with trying to control the structural noise path in that you can fix one path and the sound will just find another path. It often can travel further and more efficiently than by the airborne path. And this is the old example of putting your ear to a train rail. You can hear the train coming from miles away through the rail, whereas standing in the air, you might not be able to hear it until it's within a few hundred meters of you. Structure-borne sound or vibration then radiates into the air from surfaces in a manner similar to loudspeakers, and that's how it becomes noise. There's also a fluid-borne sound path, and I'm not necessarily today talking about underwater noise. I'm talking about pulsations of fluid. So, for example, either your refrigerants or your water stream, whatever you're using to extract heat from your system, there are pulsations in that fluid, and those pulsations will travel very long distances. It's a very efficient path. And the vibration from the pulsations is then passed to the structure, and then the structure radiates into the air as noise. Because it can go all over wherever your coolant lines go, sound can show up in very unexpected places.
York, high performance environments for life.